Hello everyone, hope you are doing very well. Today we are going to see the theory part 4 of the chapter Alcohols, Phenols and Ethers. So let's begin our today's topic. NCERT chapter 7 Alcohols, Phenols and Ethers, theory part 4th, and specifically we are going to cover today NCERT section 7.4 along with that 7.4.1. This is disclaimer. So today's learning objective, after attending this lecture, you will be able to prepare, or you can say you will be able to understand the preparation methods of alcohols. So what are the topics that we are going to cover today according to the NCERT? First of all, the section 7.4, alcohols and phenols, and in that we will cover the section 7.4.1, preparation of alcohols. We will also solve NCERT exemplar question number 7 and 8 and the example 7.2. So let's start with the alcohols preparation of alcohol, section 7.4. Alcohols can be prepared from the following method. First of all, from the alkenes. The alkenes are the unsaturated compounds containing carbon and hydrogens, and there is the presence of double bond between the carbons. So from the alkenes, you can prepare the alcohol by the hydration reaction. That means the reaction of alkene with the water molecule in presence of H positive ion. Second, when you react alkene or you do the alkenes hydroboration oxidation, then also you will prepare alcohols. Second, alcohols can be prepared from carbonyl compounds, such that if you reduce the aldehydes, ketones, esters, carboxylic acids, then you will get alcohol as the product. Third method is the preparation of alcohols from Grignard reagent. Grignard reagent is alkyl magnesium halide, RMgX. So when you react the aldehydes, ketones and esters with Grignard reagent, you will get the alcohols as the product. First of all, let's understand the preparation of alcohols from alkenes. So from particularly alkenes, how can you prepare the alcohols? And in this, the first is acid-catalysed hydration method. So from the alkenes, you can prepare alcohols by following the acid-catalyzed hydration, in which the alkenes react with the water molecule in the presence of an acid catalyst like H2SO4 or H3PO4. This reaction follows Markovnikov's addition rule. We have learnt about this, that if alkene reacts with, or if alkene undergo the addition process, then it can follow Markovnikov or anti-Markovnikov rule. But here, for the preparation of alcohols, the alkenes react with the water molecule in presence of acid catalyst to get the proton H positive. The reaction will follow Markovnikov addition rule. So Markovnikov addition rule says that the nucleophile, the R negative, nucleophile will attach to that double bonded carbon which has less number of hydrogen atom, which is less substituted, you can say. So this is Markovnikov addition rule, which says that nucleophile in this reaction will attach to that double bonded carbon of alkene which has lesser number of hydrogen atom. If you see the reaction here, we have given, let's take a unsymmetrical alkene. Let's take unsymmetrical alkene RCH double bond CH2. Unsymmetrical how? Because the double bond is present at very first carbon, right? So there is no symmetry. Now, when you add it with water molecule, when you react it with water molecule in presence of proton or acid catalyst, you will get alcohol. So OH here will act as a nucleophile, OH minus, and will going to attack on the double bonded carbon, which has lesser number of hydrogen atom. And you can clearly see in this unsymmetrical alkene, the second carbon from the two double bonded carbons, the second carbon is having only one hydrogen, the first carbon having two hydrogens. So the lesser number of hydrogen atom is present on the second carbon. So OH nucleophile will going to attach on the second carbon and you will get a secondary alcohol, right? If you take a symmetrical alkene means there is this double bond which is present at very center of your alkene. When this is going to react with the water molecule in presence of acid catalyst to get H positive, we get alcohol as our major product. But here the Markovnikov addition rule is not applicable because the alkene is symmetrical. Okay, so hydrogen present on both the carbon, on both the double bonded carbon can be same, maybe same, right? So you will get finally a major product as alcohol. This is also a preparation method of alcohols from the symmetrical alkenes. If you take a example of propene, which is unsymmetrical, CH3 CH double bond CH2. You react it with water molecule in presence of H positive acid catalyst, you will get propane 2-ol because the OH negative nucleophile is going to attach on the double bonded carbon having lesser number of hydrogen atom, which is the center or which is the second carbon, and you will get a propane 2-ol. At the second carbon you have OH group attached. Let's see the mechanism of this acid-catalyzed hydration reaction of alkenes. Step by step we will go. The step 1 includes the protonation of alkene. So we have an alkene, we do the protonation of that alkene. In this process, there is the formation of carbocation intermediate by the abstraction of hydrogen atom by C double bond C. That is pi bond. So from the pi bond, there is this abstraction of hydrogen atom which will going to form the carbocation. What I am saying? So first of all, the water molecule will react with your acid catalyst and form a hydronium ion H3O positive. Then this H3O positive is going to react with your alkene to do the step 1, that is protonation of alkene. What will happen? Because oxygen is having positive charge, the C double bond C is going to abstract the hydrogen atom from the H3O positive and you will get a carbocation because the one of the double bonded carbon will get hydrogen atom attached to it and the another will get positive charge on it. So you will get a carbocation. Okay, and there is this hydrogen oxygen bond electrons that will shift to the oxygen because it is having positive charge and you will get a H2O molecule, water molecule in this process. Okay, so in this process, including the protonation of alkenes by the formation of carbocation. The step 2 involves the nucleophilic attack of water. So donation of lone pair of oxygen, the water molecule has oxygen on present in it and oxygen has lone pair on it. So those lone pair is going to be donated of water to the carbocation. So what will happen? We have got our carbocation in the first step. Now what will happen? This water molecule having oxygen and oxygen having lone pairs over it, these lone pairs is going to attack on the positive charge of the carbon to stabilize the carbocation. Okay, and you will get a you can say protonated carbocation. Okay, because the nucleophilic attack of water is happening over the carbocation by the donation of lone pairs of oxygen atom of water molecule, and you will get this you can say protonated carbocation. Okay, so here what will happen? The lone pairs of the oxygen will shift to the positive charge of the carbon. Okay, this carbon will get satisfied, the carbon charge electron distribution will get satisfied, but here the O will get positive charge when it is going to attach with that carbon. Now what will happen? The step 3 includes the deprotonation. So we have just protonated carbocation. Now deprotonation happen, in which the abstraction of hydrogen atom by the water will happen to regenerate the hydronium ion, which we have used in the very first step, and an alcohol will produce. So we have this protonated carbocation, and what will happen? This positive charge of oxygen, okay, this is going to be stabilized. Why? Because another water molecule abstract one of the hydrogen atom from this protonated carbocation, and by the donation of this, you can say, oxygen lone pairs, and one of the hydrogen will be removed from the protonated carbocation, and the oxygen hydrogen bond electrons will be going to shift over the oxygen to stabilize its positive charge, and you will get finally the hydronium ion along with the major product alcohol. Okay, so finally you will get carbon attaching with the hydroxy group OH, and along with that you will get your hydronium ion, which we have used in the very, or which we have made up in the very first step of the mechanism of acid catalyzed hydration of the alkene. Okay, so these are the 3 steps. I hope you understand the 3 steps of the mechanism of acid catalyzed hydration of the alkenes to prepare the alcohols. Next type of reaction happens in the preparation of alcohol is hydroboration oxidation. Now what will happen in this? This is a indirect method of alkenes hydration. Okay, in the previous method we are doing the hydration by reacting it with the hydronium ion or water molecule in presence of acid catalyst, but in this hydroboration oxidation reaction, alkenes indirect hydration happens. How? So here the production of the alcohols will happen via anti-Markovnikov addition rule. Okay, so the product you will get will be the anti-Markovnikov product. This step, this reaction, hydroboration oxidation of alkenes, or you can say indirect method of hydration of alkenes, occurs in the 2 steps. First step include the hydroboration with the B2H6 molecule, that is diaborane. Its simplest form is BH3 borane, and it is stable in the B2H6 form diaborane. So second step, other than the after the first step, we have second step, which is the oxidation, because as the name says, hydroboration oxidation. So first step is hydroboration with the diaborane. Second step is oxidation with the H2O2 and NaOH. If you see an example here for the hydroboration oxidation, we have taken 3 molecules of propene. When you do the reaction of it with the diaborane B2H6, that means you are doing the hydroboration of it, and after that you are doing the oxidation process with H2O2 in presence of NaOH. Final product you are getting is an anti-Markovnikov product, and it is 3 molecules of propanol, CH3, CH2, CH2OH. Let's understand the mechanism of hydroboration oxidation reaction. Step 1 is the alkene reacts with diaborane. So here we in the previous example we have taken propene. So propene or alkene when reacts with the diaborane or borane BH3 to form a trialkyl borane, or in the case of propene, triapropyl borane. This is the first step of the mechanism. So we have propene. When you react it with the diaborane, or you can write it in the form of BH3 whole twice, and BH3 can be written in the form of HBH2. It will be easy to show that this hydrogen replacement or hydrogen shifting is happening. Okay, so you are writing BH3 as HBH2, or you are writing B2H6 as BH3 whole twice. Okay, so reacting propene with the diaborane, what will happen? The double bond will be removed. The hydrogen from the diaborane is going to attach on the carbon, or you can say double bonded carbon, which is having more number of hydrogen, because the product addition will happen via anti-Markovnikov rule, which is opposite of Markovnikov. So here hydrogen will be attached over the carbon, which is having Okay, you can say anti-Markovnikov rule says that the negative part, here HBH2, so H is positive, BH2 negative. Okay, so here BH2 negative is going to attack on the carbon which is having more number of hydrogen, and the hydrogen positive will attack on the other double bonded carbon. So you will get a monopropyl borane after the reaction of propene with the diaborane as per anti-Markovnikov addition. So hydrogen will attack on the less hydrogen substituted carbon, and the BH2 negative, the negative part of our molecule, will react or will add upon the double bonded carbon having more hydrogen. Okay, so you will get a CH3 CH2 CH2 BH2. Then what will happen, this monopropyl borane which you just get, you react it again with two molecules of propene. Why is it so? Why we are taking exactly two molecules of propene? Because if you see, we are doing the addition reaction, right? So what will happen, the hydrogen from the diaborane or borane, so we are taking HBH2 whole twice, right, as a diaborane, and then what will happen, from the BH3 one of the H will be attaching to the propene and giving us a monopropyl borane. Okay, now still we have BH2 in our monopropyl borane, right? Now what will happen, this BH2, that means B is still attaching with two hydrogens. Now these two hydrogen will be removed, okay, and is going to attach to the other two molecules of propenes. That's why we are needing two molecules of propenes here to react with monopropyl borane. So when this reaction happens, you will get a final product, triapropyl borane. So all the hydrogen of borane is attached with all the molecules of propene. So you almost, or you can say at overall you need 3 molecules of propene to react with 1 molecule of diaborane, right? And you will get a final product as triapropyl borane, that is CH3 CH2 CH2 whole thrice B. Now the mechanism involves the step 2. Step 2 is trialkyl borane, or in the case of propene, triapropyl borane you get is going to oxidize to the alcohol form, that is propanol, using H2O2 hydrogen peroxide in the presence of sodium hydroxide. So you take this triapropyl borane, CH3 CH2 CH2 whole thrice B, you react it with hydrogen peroxide to oxidize it to the alcohol. So you, from the triapropyl borane, you will get 3 molecules of primary alcohol, which is propane 1-ol or propanol. Okay, plus BOH whole thrice will be your side product. So this is how you can prepare the alcohol by the hydroboration oxidation reaction of alkenes. And this is a indirect method of hydration of alkenes because it occurs in 2 different steps, hydroboration and oxidation. Next method for the preparation of alcohol is from carbonyl compounds. So by the reduction of aldehydes and ketones. So carbonyl compounds are the compounds containing C double bond O in it. Okay. So in which there is compound called aldehydes and ketones. Aldehydes have C double bond OH and ketones have C double bond O. Both are carbonyl compounds. Okay. So by the reduction of aldehydes and ketones, you can get alcohols as the product. Aldehydes containing CHO group are reduced to primary alcohols, whereas ketones are reduced to secondary alcohols, because if you see, ketones are RC double bond OR, right? So C double bond O is present in between of 2 alkyl groups. So if there is a preparation of alcohol from the ketone, it will be secondary because that carbon is actually secondary of ketone. And in the case of aldehyde, which is C double bond OH, okay, to that carbon only 1 alkyl group is attached, 1 R group is attached. Okay, so it is going to give us a primary alcohol. What are the reducing agents which we are going to use? The catalytic hydrogenation in which we are going to use the hydrogen in presence of palladium, platinum or nickel. And the reaction involves aldehyde. So first of all, we take aldehyde, general formula RCHO. We do the catalytic hydrogenation of aldehyde with the hydrogen in presence of palladium metal, and you will get a primary alcohol after the removal of C double bond O, and you will get a RCH2OH. Okay, so from the aldehydes you will get a primary alcohol RCH2OH. The C double bond O will break and you will get a primary alcohol from the aldehyde. If you take a ketone, again you do the catalytic hydrogenation of the ketone RC double bond OR with the hydrogen in presence of palladium metal. You will get a secondary alcohol, that is RCHOH R prime. Okay, now this R or R prime may or may not be same. Continuing on this, let's talk about our second method under the reduction of aldehydes and ketones, that is sodium borohydride reaction, NaBH4. The reaction can be, if you take aldehyde and you're doing the reduction of aldehyde, you can also do it in the presence of sodium borohydride. So when you react the aldehyde with sodium borohydride, it is going to give us primary alcohol. And for the ketone case, the ketone when reacts with sodium borohydride, it is going to give us secondary alcohol. Third method under the reduction of aldehyde and ketone is lithium aluminium hydride. This is the third reducing agent, you can say, which you can use to reduce the aldehydes and ketones. The reaction, so for the aldehyde RCHO, when you react it with the lithium aluminium hydride, which is a very strong reducing agent, you will get a primary alcohol. And in the case of ketone, RCOR prime, when you react it with LiAlH4, you will get a secondary alcohol RCHOH R prime. Here also the R prime may or may not be same. Reduction of carboxylic acids. Another carbonyl compound is carboxylic acid. Let's do the reduction of carboxylic acid to get alcohol. Carboxylic acids reduced to primary alcohols by strong reducing agents like lithium aluminium hydride. Lithium aluminium hydride is an expensive reagent, and the acids, the carboxylic acids, are first converted to esters, and then esters will be reduced to alcohols by catalytic hydrogenation. If you see the reaction, we have carboxylic acid, RCO, which is the general representation for carboxylic acid. You react the carboxylic acid with lithium aluminium hydride, a strong reducing agent, and then the ester you will get, you have to react it with water molecule to reduce it to alcohol, RCH2OH, and you will get a primary alcohol as the product. Now, there is this carboxylic acid, RCOOH. When you react it with another alcohol, R prime OH, in the presence of proton or acid catalyst, you will get RCOOR prime, that is ester. Then this will react with the hydrogen molecule in the presence of catalyst, and you will get the major product, the primary alcohol RCH2OH plus R prime OH. So you will get two alcohols. Okay, the one alcohol will contain the same number of carbon which is present in our initial carboxylic acid. The another alcohol you will get a one lesser carbon, will going to have a one lesser carbon compared to the reactant carboxylic acid. So two alcohols you will get, one from R, another from R prime. Okay. Reduction of esters. Esters can be reduced to the alcohols by doing the catalytic hydrogenation or in presence of lithium aluminium hydride. This produce two molecules of alcohol, So if you take the ester, RCOOR prime, R and R prime may or may not be same. When it reacts with water molecule in the presence of palladium to do the catalytic hydrogenation, or this can also happen in presence of LiLH4, you will get two molecules of alcohols, RCH2OH plus R prime OH. One is from the R alkyl group and another alcohol is from R prime alkyl group. Okay, so you will get two molecules of alcohols. Now, in the presence of LiAlH4, if you do this reaction, the similar products you will get. The ester will react with lithium aluminum hydride, and then you have to react it with the water molecule, and you will get finally two molecules of alcohols, RCH2OH plus R prime OH. There is note. The note is that sodium borohydride, NaBH4, which is a mild oxidizing agent, cannot reduce acids and esters. Okay, so NaBH4 is a mild oxidizing agent and it cannot reduce strong acids and esters, which require stronger reducing agents. Okay, so NaBH4, that is sodium borohydride, we don't suggest to use as a reducing agent for the acids and the esters. Let's see our next method for the preparation of alcohols, that is from Grignard reagent. The Grignard reagent is alkyl magnesium halide. This will react with carbonyl carbon to form an adduct. Hydrolysis of this adduct formed will yield finally an alcohol. So let's take the example of reaction with formaldehyde, the simplest aldehyde. Grignard reagent RMgX reacts with formaldehyde to give an adduct. The hydrolysis of that adduct will going to produce a primary alcohol because formaldehyde is an aldehyde. If you see the example of the reaction given, we have formaldehyde HCHO reacted with RMgX. What will happen? You will get a adduct. So this RCH2O MgX will be the adduct. Okay. So formaldehyde will give a adduct after the reaction with Grignard reagent, and this adduct further on the hydrolysis with the water molecule gives us a primary alcohol, plus MgOHX will be removed as a side product. Okay. So RCH2OH, the primary alcohol you will get after the reaction of formaldehyde with Grignard reagent, and the adduct you will get is going to hydrolyze with the water molecule and you will get a primary alcohol. So this is how you can prepare the alcohol from Grignard reagent. Reaction with aldehyde. So Grignard reagents RMgX reacts with the aldehydes other than the formaldehyde. Okay, because formaldehyde is the simplest aldehyde you are having, okay, which is giving us a primary alcohol after the reaction with Grignard reagent. So Grignard reagent, when reacts with the aldehyde other than formaldehyde to give an adduct, and the hydrolysis of an adduct produces a secondary alcohol. So what does it mean? It means that only there is formaldehyde which is aldehyde. Only aldehyde is formaldehyde which is going to give us a primary alcohol after the reaction with Grignard reagent. All other aldehydes is going to give us a secondary alcohol after reacting with Grignard reagent. The reaction is, you take a aldehyde RCHO reacted with R prime MgX, a Grignard reagent, you will get RC R prime HO MgX, which is an adduct. Now this adduct, when undergoing the hydrolysis process with the water molecule, it is going to produce secondary alcohol, because here you can clearly see OMgX, right? OMgX is present in the adduct, so MgX is going to be removed from here, and the or you can say mgx is going to be removed from here, and the OH is going to be present at the carbon. The carbon, which is secondary carbon, because that carbon is attaching with two other R groups, may or may not be same, but two other carbons, right? So that carbon which is bonding with OH is bonding with other two carbons. So this is a secondary alcohol. So only formaldehyde is the aldehyde which produce primary alcohol. All other aldehydes after the hydrolysis and after the reacting with Grignard reagent and hydrolysis process gives us secondary alcohol. Now let's take the another carbonyl compound, that is ketone. So when reaction of ketone with the Grignard reagent happens, it gives us an adduct. And then the similar thing, the adduct will undergo the hydrolysis process to produce a tertiary alcohol. Now ketones gives us a tertiary alcohols after the reaction with Grignard reagent. If you see the reaction, we have ketone RC double bond OR plus R prime MgX, which is a Grignard reagent. They react with each other, forms a adduct RC R prime R O MgX. And when this adduct undergoes the hydrolysis process with the water molecule, you will get a tertiary alcohol because the OH which is attaching with carbon is attaching with other three carbons. That carbon is attaching with other three carbons. So this is a tertiary alcohol. Plus MgOH will be your side product. Okay. So formaldehyde gives us primary alcohol, other aldehydes gives us secondary alcohol, and ketones gives us tertiary alcohol after the reaction with Grignard reagent and hydrolysis process. Let's see the mechanism steps of the reactions we have seen from the Grignard reagents. The step 1 is nucleophilic addition of Grignard reagent to the carbonyl compound, or you can say carbonyl group, C double bond O. So what will happen? The C double bond O is present in our all carbonyl compounds, whether it is ketones or aldehydes, right? What will happen when they reacts with RMgX? Because there is charge distribution, or R and magnesium bond is polar, due to which there is partial negative and positive charge over R and magnesium. Okay, and R is a alkyl group. Okay, so it will also show its effect and gets a partial negative charge. Now what will happen? The C double bond O present in our carbonyl compound, because there is electronegativity difference, the oxygen is more electronegative. So the double bond electrons will shift towards the oxygen. Carbon will get a positive charge. Now what will happen? It will act as an electrophile. And because R from the RMgX is having partial negative charge, it will act as a nucleophile. And nucleophile addition of Grignard reagent, that is R group, happens, and then this R group is going to attach with the carbon of the carbonyl group, and you will get an adduct, that is CR O negative MgX positive. Okay, so this is what happens in the first step when the reaction of carbonyl group or carbonyl compound happens with the Grignard reagent. Okay, so nucleophilic addition of Grignard reagent happens to the carbonyl compound, carbonyl group, and you will get an adduct. Step 2. Step 2 involves the adduct hydrolysis, or you can say hydrolysis of magnesium alkoxide complex, which is actually adduct. So you take the adduct, you do its hydrolysis, what will happen? You will get your alcohol, CrOH, and C is also forming other two bonds. It can be hydrogen, it can be R groups. If there are R, if all the bonds are attaching with the carbon, which if the carbon attaching with hydroxyl is attaching with other bonds via other bonds with other alkyl groups. Okay, so this is OH, which you are getting in the alcohols. Okay, now this OH is attaching with the carbon, and the carbon is making other three bonds other than the OH bond. Okay, so carbon OH bond is the one bond. Other three bonds, if the other three bonds are with the R group, then it is a tertiary alcohol. If other three bonds are hydrogen, okay, then it is a primary alcohol. And if the carbon, other three bonds, from which two bonds are R groups and one is H atom, then it is a secondary alcohol. Okay, plus side product will be MgOHX you are getting in this reaction. So this is the two-step reaction happening. Carbonyl compound, whether ketone, aldehyde, they are reacting with the Grignard reagent. So step 1 is nucleophilic addition of Grignard reagent to the carbonyl group, and you will get an adduct. And the step 2 is the hydrolysis of adduct in the presence of water molecule to give you a particular or suitable alcohol as the main product. Let's solve an example. 7.2. Example is, give the structures and IUPAC names of the products expected from the following reactions. So we have given three parts. A. Catalytic reduction of butanol. B. Hydration of propene in the presence of dilute sulfuric acid. And C. Reaction of propanol with methyl magnesium bromide followed by hydrolysis. So you have to give the structure along with the IUPAC name of products that is going to form in all these three reactions. Let's see the first reaction, catalytic reduction of butanol. So for the catalytic reduction of butanol, what will happen? The catalytic reduction is going to reduce the butanol to butane 1-ol. Butanol is actually an aldehyde. Okay. The Al in the end suffix represent the aldehyde group. So butanol is reduced to the butane 1-ol after the catalytic reduction. So if you have butanol, CH3, CH2, CH2 and CHO, the aldehyde group, when you do its catalytic reduction with the hydrogen in presence of palladium metal, you will get butane 1-ol from the butanol. The product is a primary alcohol because OH is attaching with the carbon, which is attaching with other one carbon only. So it is a butane 1-ol is a primary alcohol. Also, its parent chain contain four number of carbons. That's why the name has butane. Okay, and there is no substituent. Only there is one substituent, which is OH present at the first position carbon. So therefore, if you write the IUPAC name of the product, it will be butane 1-ol. The E of the butane is replaced by 1-ol. Similarly, for the second reaction, which is hydration of propene in the presence of dilute sulfuric acid. Propene hydration, if you do in presence of dilute sulfuric acid, it will give propane 2-ol. So let's take the reaction. We have propene, CH3, CH double bond CH2. You react it with dilute sulfuric acid. It is going to give us propane 2-ol. The product you are getting is a secondary alcohol. Okay, so this reaction happens. So double bond will break and the OH negative, the nucleophile, is going to add on the double bonded carbon, at which the hydrogen is lesser in number as per the Markovnikov addition rule. Okay, that's why you are getting a propane 2-ol, a secondary alcohol. Now here in the product, the parent chain is 3-carbon parent chain, which is propane. And the substituent is OH group, which is present at the second position of the chain. So the IUPAC name of the product is propane 2-ol. Next, for our third reaction, that is reaction of propanol with methyl magnesium bromide, that is Grignard reagent, followed by the hydrolysis. We just have studied about it. So if you react the propanol, which is a ketone, with the methyl magnesium bromide Grignard reagent, So ketone yields a tertiary alcohol. Okay. So it is going to yield 2-methyl-propane 2-ol. So you have this propanol CH3 C double bond O CH3. You reacted with methyl magnesium bromide CH3 MgBr in the presence of ether. You will get an adduct. Okay, because the nucleophilic addition of the methyl magnesium bromide over the propanol happens and you will get an adduct. Now this adduct undergo the hydrolysis process in presence of water molecule and you will get finally a tertiary alcohol as the major product, which is 2-methyl propane 2-ol. Okay, OH attaching with the carbon which is attaching with other 3 carbons. So this is a tertiary alcohol. So the product is actually a tertiary alcohol. The parent chain in the product is 3-carbon chain, which is propane. And if you talk about the substituents at the same carbon, so we have one methyl group and one OH group attached on the same carbon, that is second carbon in the 3-carbon chain propane, which is parent chain. So the IUPAC name of product will be 2-methyl propane 2-ol. Okay. Let's solve an NCERT exemplar question number 7. Question is, give the IUPAC name of the compound given below. So we have given the image of a compound CH3 CHCl CH2 CH2 CHOH CH3. You have to write the IUPAC name of it. Options are 2-chloro-5-hydroxyhexane, 2-hydroxy-5-chlorohexane, 5-chlorohexane 2-ol, or 2-chlorohexane 5-ol. So for this question, the correct answer is option C, 5-chlorohexane 2-ol. So if you see the given compound, firstly you have to, according to the IUPAC nomenclature, firstly you have to identify the parent chain which is containing the largest number of carbon and also the carbon which is attaching with OH. So we have numbered. After that, you have to number the parent chain, right? And the lowest possible number should be given to the carbon which is attaching with OH group. So you have done your numbering and the OH group is attaching at the second carbon. So parent chain is hexane, 6-carbon chain. The location of functional groups, we have hydroxyl groups at the second carbon and chlorine atom at 5th carbon. So IUPAC name will be, first of all, your substituent names in the alphabetical order. So 5-chloro and then the word root hex, then first suffix, primary suffix, that is ane, and then secondary suffix, that is 2-ol. So this is the IUPAC name and hence our correct answer is option C. Let's see the next NCERT exemplar question number 8. IUPAC name of metacresol is, we have studied about it, okay? So options are 3-methylphenol, 3-chlorophenol, 3-methoxyphenol, or benzene 1,3-diol. So the correct answer for this question is option A, that is 3-methylphenol. If you talk about the structure of metacresol, this is this given structure. So we have phenol, and at the third position or at the meta position of the benzene with respect to the OH group, we have methyl attached. So that's why the name is metacresol. Now this is the common name of this molecule. If you write the IUPAC name, you have to tell about the parent chain, which is actually phenol. And the substituents, they are methyl group, that is CH3 group, present at the meta position of benzene or the third carbon. So IUPAC name of metacresol is 3-methylphenol. Okay, let's see the summary, the points to remember from the today's lecture. So we have seen the preparation of alcohols, phenols and ethers. Firstly, from the alkenes by doing the acid-catalyzed hydration in presence of H2SO4 or H3PO4 follows Markovnikov's addition rule. Then the another method from alkenes is hydroboration oxidation of alkenes with the diaborane followed by the oxidation with H2O2 in presence of NaOH, and it will going to give us a anti-Marconico product. Second method preparation of alcohols is from carbonyl compounds. So such like aldehyde reduction, or you can say aldehyde reduction if you do, you will get a primary alcohol. From the ketones you will get secondary alcohols, and the lithium aluminium hydride, which is a strong reducing agent, can reduce carboxylic acids and esters, but sodium borohydride cannot. Okay, and ester reduction, if you do the ester reduction, it will going to produce 2 alcohol molecules. Third method, preparation of alcohols from Grignard reagent. So RMgX, alkyl magnesium halide, reacts with the carbonyl compound to form alcohols. The formaldehyde is the only aldehyde, that is HCHO, which gives us primary alcohol after the reaction with Grignard reagent. The other aldehydes gives secondary alcohol, and ketones actually produce tertiary alcohols after the reaction with Grignard reagent. Okay, thank you. That's all for today's chemistry session. Thank you.